Welcome back to the lecture series on electric motor and generator design. This is lecture number 2, and the purpose of this lecture is to acquaint you with the overall operational theory in practical terms for the 3 kinds of motors that we're planning to study in this series. This is the motor genealogy chart that we listed before, and we're going to study this induction motor, which is electronically controlled, and we're going to study this reluctance machine, which are electronically controlled, and then we're going to study both hybrid and permanent magnet, no, wait a minute, they're over here. Brushless DC motors over here we're going to study. Both sine drive and square drive, electronically commutated, okay? Then induction, we're going to show you how to design rotors for those to get good performance with a stator. This is a very interesting slide that compares machine cross sections to give you an idea what these three machines look like in concept anyway. This was developed a number of years ago by Professor Tim Miller from the University of Glasgow, my co-author for a couple of books we've written on brushless machines. But you'll notice that this little chronology starts with the commutated DC motor. Here's your field windings in the stator, and then your armature windings on the rotor. And those are the commutator bars there, and these represent the brushes. So each one of these coils is here's one pole, there's a second pole. So that means that the coils are going to be wound across 180 degrees apart. It'll be a coil there and a coil there, and then pairs of those coils wrapped, stepped all the way around in a lapped fashion. So as this rotor rotates, see, when the current is applied into those coils, it causes the polarity of those coils to be such that they move. That will put that torque component on the conductor, which pushes against the steel teeth of the rotor and causes it to rotate. So it commutates itself, it rotates, but then as soon as it rotates, why, it shorts out the next bar and energizes the next coil and shorts out the one before it. So rotation is continued. If you reverse the polarity of the voltage across these two terminals or across these two terminals, you change the polarity of the flux generated by either the stator or the rotor. If you have permanent magnets here, then you just change the polarity of the armature. Now, what's interesting to note, even by looking at this picture, is down here we have a permanent magnet version of this. Here's a permanent magnet version of that. Instead of this wound electromagnet, North Pole and South Pole here, we have a permanent magnet. Now, there's no wires connected to that, so the flux from this permanent magnet is fixed. The field, or the flux that comes from this electromagnet, can be adjusted. So if you connect a DC power supply across here, you can vary the strength of this field and vary the whole torque speed curve and characteristics of the machine. But on the permanent magnet machine, you don't have near that flexibility because your magnetic field is fixed. It's not adjustable. You can't make it stronger or weaker. But these DC motors evolved into synchronous motors. Remember, that was our second motor. It was an AC synchronous motor. It has a wound field on the rotor, much like the wound field on the stator of a DC machine. So this rotor produces DC current flows in these coils, producing north-south poles, and then the flux from those electromagnet poles in the rotor link with the conductors in the stator, so you have a synchronous motor. The brushless version of that's this one, replaces these wound field coils with permanent magnets, the same way that in the DC motor, the permanent magnets in the stator replace the wound electromagnets in the stator. In the case of the synchronous machine, the wound poles in the rotor are replaced by permanent magnets on the rotor. So that's why it's called a synchronous machine, even though originally it was called a brushless machine, because it originally was an inside-out version of this machine, which we'll see in an upcoming slide. Now, take this same motor here with the magnets on the surface. This is an SPM, surface-mounted magnets, we call those. If you take the rotor core and put slots inside of it, instead of having the magnets on the surface, you stick them on the inside. You have, that's now known as a brushless permanent magnet AC machine, or permanent magnet synchronous machine. And so you get torque from the magnets, but you have some little steel poles in between the magnet poles here, and you can vary how big those are. You can adjust the reluctance torque component you get from those poles that are those soft iron poles that are between the magnets. Didn't mean to flip that slide so quick, but since we did, we've got to start talking about this. These motors are, well, maybe I could go back. Yeah, let's go back and finish this. Let's do it that way. That's better. In this case, the last thing I wanted to show you about this was of course the induction machine, which has the same stator as this guy, but it has a different kind of a rotor in it. And we're going to talk about what that rotor consists of. That's a punch lamination with slots in it, and those slots are filled with current-carrying conductors. There's a couple ways you could fill it. You can wind them, or you can cast them in there. Now, this machine here has the same kind of a stator as these other machines we talked about. See, they all have the same stator, but the rotor is different. It's made up of pieces of steel and air, or steel and plastic, or steel and magnets even. But so the steel part are called magnetic flux carriers, and the air sections, or plastic sections, or fiberglass sections, or whatever you want to make them out of that's non-magnetic, those are called flux barriers. So if this is a direct axis, the inductance of the phase windings in this axis are high because there's lots of iron in the circuit, but in quadrature, or 90 electrical degrees, this is a 4-pole machine, so it's 45 degrees mechanical. This is a quadrature axis, so the inductance of the phase is low in that axis because there's a lot of flux barriers radially from the shaft out in that quadrature direction, you see. And now here's an extreme example of a reluctance machine that has poles that look like a gear on the rotor and poles that look like gear on the stator. So if you look at this winding here, the flux is going to go through there like that. There's very little air gap in the circuit. It's all iron, very tiny clearance gap there. But in this set of poles, there's lots of air gap in the circuit. You got this great big air gap in there. So the inductance here is very low, and the inductance there is very high. There again, we're in quadrature here. So in reluctance machines, the torque and performance you get is based upon how well you can create this saliency, or how well, or how big of a difference you can design into the geometry such that the one inductance is a lot higher than the other one. So the inductance ratio is equivalent to the saliency ratio in these kind of machines. So that's what I wanted to point out. But we're not studying the switch reluctance machine in this series because it uses a different stator, different winding. It's a whole different design topology. So it's not easy to compare it with these other machines. We'll have to treat that as a separate topic all by itself. Okay, now the purpose of using these old motors in new ways using power electronics is to vary the speed and determine whether the torque or speed is positive or negative. So if we plot torque on the horizontal axis, and here's zero torque, so we can produce clockwise torque or counterclockwise torque. That's like pedaling your bicycle frontwards or backwards. All right, now the wheels, then, if you apply a torque, the wheels are going to turn, the motor's going to turn, so we'll define clockwise speed as positive and counterclockwise speed as negative, just like we define clockwise torque as positive and counterclockwise as negative. So you can look at the combinations you can have. I can be going clockwise and producing, as I accelerate, I'm producing positive speed and positive torque. So once I've accelerated up some speed, I keep going to that speed, and torque and speed are both positive. But now I want to slow down, so I have to, even though I'm going the same clockwise direction, so I'm still traveling, but as I slow down, I've got to apply a negative torque to slow down. So we're operating in this quadrant when torque is negative with positive speed. Of course, the same explanation works for these other three phases, other two quadrants. Negative torque, negative speed means I go backwards. You put your car in reverse, you're applying reverse torque, and you're going reverse speed. You're going backwards. And here's a case where if I'm going backwards and I want to change from going backwards to start slowing down, then I've got to apply positive torque as my speed decreases. Here's another way to look at the same concept, and that is to draw a picture of a shaft, put a shaft in it, put some arrows on it. A black arrow means torque, or means speed, and the transparent arrow is torque. So as you can see in each quadrant, in quadrant 1 you've got clockwise torque and clockwise speed. Quadrant 2, when you're braking, you've got clockwise speed, but you've got counterclockwise torque. So that's kind of handy. It's good to have this thought in your mind. These are concepts that need to be in the back of your mind before you design a motor. In my opinion, they're more important than how the inverter guy is going to drive your motor. You need to know a little bit about that, but not near as much as he does. Now let's look at this picture here. This is a very important picture for motion control. And a lot of these electronically controlled motors are used for applications like this. This concept is applicable to accurate angular positioning of a shaft with big inertia loads or low inertia loads. This picture is applicable to all linear motion applications. So that it's been proven long ago that the most efficient positional move is accomplished if the shape of this velocity profile is in the shape of a parabola. We're not going to prove the mathematics of that, but that's easily proved. A parabolic positional move is the most efficient, takes the least amount of power. Now, the area inside a velocity profile like this, if you integrate this, calculate the area inside, that's the angle that the rotating shaft went through, or it rotated through. So that part of that time you're accelerating, that's positive torque and speed. That's all right. Now here we're up to a speed. And by the way, this sort of a trapezoid is a very close approximation to the shape of a parabola. I guess I should have drawn one on top of here. But for a positional, angular positional move, a parabolic move is the best, but a trapezoid makes it easy to control. So a third of the time, to make the trapezoid approximately the same shape as we could accelerate slower. We would come up to like this and hit a point, and then decide we have to stop, and then reverse torque, make torque negative, and stop and come down till we get to here. So we'd have a triangular move where the area in this peak of the triangle equals the two areas we lose over here. Now, if I could accelerate in 0 time and get to a lower speed and stop in 0 time, and the area underneath that rectangular move would be equal to the same area as this. So you could go through that angle in those extremes. You come up at 0 time, hit a lower speed, and stop at 0 time. You can take the maximum acceleration time and do a triangular move. But the area of the triangle, the area of the rectangle, and the area of the trapezoid, they all have to be equal. And of course, when you accelerate, you overshoot. So you're going to have some settling time there. When you stop, all of a sudden, you got a big inertial load, you're going to overshoot. You'll get some ringing due to the compliance. So you might need dampening in the circuit, which is friction. All those things taken into account. But this type of a move demonstrates the importance of positive and negative torque. Negative torque is always braking torque. Same thing in a car. A car accelerating here. It's going along the highway. When you stop, you come out to this speed. Now, historically, we've only used friction brakes in our car to stop the car. But with the hybrids, they don't rely just on friction brakes. They use the regenerative or the generating ability of the traction motor in a hybrid vehicle to convert some of that stopping energy to electricity and recharge the battery. It's interesting that diesel locomotives, they can't do that. When they decelerate or stop a train, the generators connected to the diesel engine, they generate a lot of power, but they can't put those back. They can't convert that back to diesel fuel. They can't. So they have to put big resistor banks on top of the locomotive to convert that energy to heat. Now the basic theory involved with all electrical machines, we assume that most, if not all of you, have some understanding or a grasp of that. You get it all in a first course in electric machines and drives. And Professor Ned Mohan from the University of Minnesota has written a very excellent book on this that's used by a lot of universities around the world to teach these fundamental concepts. And the concepts that he teaches, of course, are Maxwell's equations and Biot-Savart's law and Lorenz's law and Ampere's law and Faraday's law to describe all these effects of electro and magnetic fields. Maxwell put them all in nice, clean mathematical relationships after others before him had put forth the theories on them, but he did all the mathematics to prove that their theories were true. But for the balance of this lecture series, we're going to study the three machine types and how they're powered and how they're controlled, and see what their differences and what performance differences there are based on the techniques used. This is particularly true of the brushless machines. All of these machine types produce their torque as a result of the magnetic flux linkage between the rotor and stator in that air gap. We've said that before. And this inside the air gap, we're converting the energy, and we're going to make a lot of use of that when we get around to sizing a machine from scratch. It's really quite amazing that you can get so much force created in air, and it's the magnetic field that's created by either electromagnets or permanent magnets that creates that stress. I think if you look at the air gap stress in electrical machines, we're going to study that later, but the highest ones that I've ever seen put out 35 pounds per square inch of air gap stress. The ones in your house, the motors that are used in your refrigerators and your washer and dryer and your household appliances, they're in the 1 to 2 psi air gap stress requirements. And what that is a force is created in the air gap times the radius of the air gap is the torque on the shaft. So the stress is that force generated, or the torque generated, converted to a force by dividing the radius back out, and then dividing that force by the swept air gap area. That would be pi d times length, and we're going to look at that again later when we're sizing machines. But that's the air gap stress we're talking about. So all machines require a magnetic circuit that part of the circuit's in the stator and part of it's in the rotor. And in the case of salient pole machines, they only have one magnetic source, and it's in the stator. All the other non-salient pole machines have two magnets, one in the stator and one in the rotor. Now, what are the sources? What are the possible sources of magnetic fields? Well, permanent magnets can provide magnetic fields, or the phase windings, the electromagnets, can create magnetic fields. This is the classical set of pictures that we see that describes the forces on a conductor with current flowing in the conductor moving in a magnetic field. And I think we've all studied this many times. But there's some interesting things to note about this. The thing that I note about it, this picture doesn't tell you where the field comes from to create this north and south pole, and from the previous slides you could readily see that either comes from another electromagnet, a coil's wrapped around these pole pieces, or it comes from maybe this is a magnet. Maybe that's a big north magnet and this is a south pole, and back here mysteriously somewhere these poles are connected together to give you a closed path. Those details are left off of this and left for you to understand, because we're just looking at what happens in where this force comes from, you see. But the other thing is, with this big a gap, this B field here is going to be awful weak, so there's got to be something else here. There's got to be some iron inside of that, and if you create a big force, 100 Newton meters or something like that on a wire, well, it's going to bend. You got to have something to support it. So this is good for the mathematics, I guess, but it's not good enough for me for a conceptual visualization of what's going on inside the motor. So I'm going to kind of twist that around a bit and think of it in terms of a concept here that maybe we can better get our arms around. You remember in the first the first lecture series, I showed a coil that had current flowing through it, and a magnetic field, a donut-shaped magnetic field, was produced as a result of each turn, and then we put some iron inside of it, and this said coil there, and here was this iron core that collected all the flux. Well, I'm going to use that same picture here for illustration purposes and replace the coil with a magnet. So we're cutting this thing apart here with a hacksaw, and we're going to stick a magnet in there. So you got a north pole there and a south pole there. So we got flux flowing around here like this, you see, and it jumped across this air gap, you see, and we're defining the air gap. So now let's conceptually turn the elements or the components of that circuit into a couple electric machines. And I've shown, for illustration purposes here, a brushless motor circuit of two types. One we call slotted, and the other is slotless. Now this slotted one, it's got the conductors in there, all right. They're in, but they're not in the air gap. The conductors are not in the air gap like the previous slide shows. Those conductors are in the air gap between the north and south pole, but they're not in there. Those conductors are wrapped around a soft iron pole piece. They're wrapped around a piece that looks like this. And the air gap, these two teeth here represent the pole faces of this air gap. So that where are the forces on this wire? It's really I guess they're there, and mathematically they're still correct. But what these conductors do is they magnetize this tooth here, and let's call this a north pole. Let's call that a north pole. Let's call that a south pole, and that's the way it would be magnetized if I have the one sides of a coil in there going from there to here. So that if this is north and that's north, there's a repulsion there. If this is the south pole, then there's an attraction there. So we get repulsion on the trailing edge and attraction on the leading edge, which causes this thing to want to rotate clockwise. You see, this is pushing it and this is pulling it, attracting and repelling. So it's very easy to see how torque is produced in a machine when you look at it that way. But to be fair, I want to make sure that I'm not trying to disprove Faraday's law there. I want to show, or any of the other laws, I want to show the same motor with the same rotor, by the way. Maybe the pole's a little thicker, but similar cross section, except I've cut the teeth out. There's no teeth in between here. So the coils are kind of spread out uniformly. They're laid around here. So now what was my air gap, here's the air gap in this concept from the previous lecture. Here's the air gap in this one. You see it there? Now our air gap goes from the OD of the magnet to the ID of the stator core, same as it went from here to the tooth. Now the conductors are really in the air. They're right in the air gap. So now we can readily see that the data on the previous slide applies to this directly, that there's actually, here our magnetic field, B, goes from here to here, just like it did in the previous slide, excuse me. Goes from north to south here. So there's a force created on that. The current's the right polarity that's going through that coil. There's a force on that wire. But the stator can't rotate, so according to Newton's law, there's a reacting force against the rotor. So it's the rotor that moves, and the field moves with it. So that's why you got to commutate. As soon as it moves over here, I've got to change the polarity of the current in the new coil that's under that pole to keep it going. So this one's attracting and that one's repelling. So when I get over here, when this moves around and covers these two coils, I've got to have this one repelling and that one attracting to keep it going in the same direction. So even though there's forces on there, according to the previous slide, there's still this attracting and repelling force. And to me, that's easier to get my arms around to think of it like that. In the case of an induction machine, it's very similar, but a little different. Let's go back and take our transformer from the previous lecture series, and we've got a core here, laminated core of steel, and we've got a primary. I showed the primary here, and a secondary winding there. So if I put an AC voltage in the primary, I'm going to generate by the magnetic induction. I'm going to generate a voltage in the secondary that, and the magnitude, the peak and the RMS values, is going to be based on the ratio of the number of turns in the primary and the secondary. If I have 100 turns on a primary and I got 100 volts, 110 volts in a primary, and I got 50 turns on the secondary, then I'm going to get 50 volts across the secondary, etc. Now let's go to the next slide. Let's take that same transformer. Let's take a big hacksaw. Let's cut it in half. I didn't get these two cuts lined up, but they're supposed to be lined up. So we cut this in half. So we got a little air gap there. And now I've got the primary on this side. I don't know why. Secondary on this side. And I short this secondary. And this shows 4 turns there, but there's really only, in a shorted secondary, there's really only 1 turn. But there's, consider these different bars all in parallel. But anyway, if then we were to somehow put a shaft in here and put an axis of rotation there and allow this thing to rotate around there and add some more coils and some more poles, well, that we would turn that into a machine that looks like this. And so There's our stator with the windings in the stator, 3 phases, and there's our rotor with the bars that that form that shorted turn. And if this is a 2-pole motor, then half of these bars, the current's coming out of the screen, and the other half of the bars, the current's going into the screen. And so it's just one shorted turn there with a bunch of conductors as a parallel path. And so there's the current that flows into the stator magnetizes this circuit, and since it's an AC current, and if you load this thing down, you're going to get some slip, and so that means you're going to induce some current to flow into the bars here, which is going to create the right polarity of flux to give you a torque due to the flux linkage of the ampere turns from this field from the ampere turns from that part of the ampere turns from this field. Okay, now we're going to move from that over, get to the brushless version of this eventually, and we're going to do that by just stopping for a minute and looking at the permanent magnet DC motor that had the field produced by permanent magnets. Remember, the induction motor has both fields produced by electromagnets. The PM machines have one of the fields produced by the magnets and the other one produced by the electromagnet. So when we take this machine and flip it, we just put the stator on the outside and the rotor on the inside mounted on bearings. We have the same thing. We cut this in half and made 4 poles instead of 2. But so you got a North Pole here. The flux flows around like this for each one of these. Everybody knows that. You guys all know that. And this guy's been around over 100 years. This has been around 60, 70 years. The brush has been around 35, 40 years. And these originally were all grid powered. These were originally all powered by batteries. Cars use these kind of motors even to this day. 50 to 75 of these are used in every automobile on the road right now. But hybrid vehicles for traction, they'll either use this kind of machine or this kind of machine, because you can drive them with electronics and get them to do things that you couldn't get them to do before. And we're going to study that in a minute. Here's another very useful view of a cutaway of the induction machine. Now, this happens to be a single-phase induction machine, which we don't use for inverter-driven applications. This is like a machine that might be used as a washing machine in your house. Here you see the rotor, and it's die-cast with copper conductor or aluminum conductors down these bars. This is a cooling fan, and this is your stator with 2 phase windings in it. This got a centrifugal switch because it's operated with single-phase power, but it's really wound for 2 phases, so it'll start. So it starts as a 2-phase motor, and then when it gets to a certain speed, the starting winding is through a centrifugal switch is opened. The circuit's open, so no current flows into the start winding, and it just runs very inefficiently with only 1 winding. Here's some space vector diagrams to help us think about these machines. Here's a classical DC machine with the wound field here. Here's your 2 stator coils. It creates the DC field there, and here's your commutated with 2 brushes. Here's the 2 brushes, and these are commutated. So the field is this way, and the current is put in that way. Here's a brushless version of that, where the field is created by the permanent magnets. So 90 degrees away is where the current is applied to the stator. And as you can see, you get the maximum torque, maximum voltage when the center of the coil span of the stator coils are right over the center of the poles of the rotor. And this is a synchronous machine, always runs like this. If I rotate this field in the stator, if I rotate that field either continuous sinusoidally or stepwise in 60-degree increments like you do in a brushless machine, these rotor poles are going to stay in synchronization with that up to the capability, the torque capability of the machine. Now, the induction motor works differently. It still has two magnetic fields, and the current and the field need to be 90 degrees apart. But if they're exactly 90 degrees apart, no current flows in the rotor bars, so that so that you won't draw any torque. So the stator current, that's this vector right here. There's the stator current. That consists of two vectors. One is the current it takes to magnetize, to create the B field, to magnetize the magnetic circuit. And the other vector is the current value that flows in the rotor to produce torque. And so both of those currents have to be supplied by the stator and by the power supply, by the power source. But what's interesting about this is that there has to be slip. In other words, this represents the speed of the rotation of the electric field in the stator, the same way the field rotated in the brushless machine. That's the synchronous speed of the stator. And in the case of a two-pole motor at 60 hertz, this would be rotating at line at 60 hertz. It would be so the RPM of that stator field would be 3,600 RPM. 4-pole be 1,800 RPM. 8-pole would be 900 RPM. A mathematical relationship. But the actual rotor doesn't go that fast. It goes slower than that. It has to go slower than that. And you notice here that what's interesting here is you see these currents flowing into the paper and out of into the screen and out of the screen. Okay, and the rotor is flowing into these bars and out these bars, you see? And those are 90 degrees approximately, not exactly. See, this is not 90 degrees. But normally it's 90 degrees. In synchronous machines, the current is 90 degrees to the B field, but in an induction motor, it's a little less because of the slip. And the only way to get slip is to load this thing down, so you slow the rotor down so the rotor is going slower than the stator field. And the difference between those two is called, the percentage difference called the slip. Now, this isn't as good a picture as one I got coming up, but this shows the magnets on the rotor as glued on there. They're part of the rotor and they don't slip, they don't move. But in the induction machine, they're not glued on there, they move. And so, but before we get into that, I'll cover that I have a better slide to show that with. I want to go back to the brushless just for a moment here and show you how this terminology of PMDC to BLDC came about. It was Erland Persson, a famous motor guy who passed away a couple of years ago. He's a very famous guy. He taught a lot of us how to design brushless motors. And him and his team at Lecture2 in Hopkins, Minnesota, I believe, wrote a servo handbook, a very famous handbook. It's been over 100,000 of them printed now. I say 80,000. It's been more than that. And distributed all over the world, very famous. And he showed this classic picture in there that shows a brush-type permanent magnet DC motor with the magnets on the outside. And this was called a PMDC motor, as opposed to shunt or series DC motors. They use the term permanent magnet DC motor. And so it was mechanically commutated. It mechanically commutated these coils to keep the flux linkage proper, to have continuous clockwise or counterclockwise rotation. Get the flux linkage between the ampere turns of the armature to the B field of the stator or the magnets. So when they first started talking about brushless machines, their draftsmen, their artists, just reversed this. They put these arcs on the rotor, and they turned these slots inside out and made a stator out of it. You see. And you don't even make a brushless motor that looks like that, but it's conceptually. So it's an inside-out brushless motor. So the word BL stands for brushless DC motor. So that's where BLDC comes from. It had nothing to do with what the shape of the back EMF is. A lot of people think it did, but it had nothing to do with that at all. In fact, what you concentrated on when you designed these brushless motors in those days was to get a high winding factor, high efficiency, and low losses and good performance, and you didn't good torque versus amp you wanted to keep the losses as low as possible, and you didn't really care all that much what the back EMF looked like. It wasn't important. If you drive this motor, if you drive either one of these motors, spin them, and look at the output voltage, you see what the back EMF is. It's very easy to see. You see the back EMF in an induction motor, but you can in these synchronous brushless permanent magnet machines. So that's where the terminology came from, was as it was converted from an inside-out DC motor. Now, Faraday's law came first, so and he concentrated on generators. So there's a definite relationship between the voltage produced and the torque produced of a machine, and the PM machine. That's very, very useful, because in Newton meter and radians per second units, it's the exact same number. The torque per amp in Newton meters equals the volt seconds per radian of the voltage constant. So that is all based on Faraday's law, and it works out that way for those machines. Now, a reluctance machine works differently than the brushless or the induction, because it has saliency. What does saliency mean? Let's talk about that for a minute. We're back to our transformer core here with a coil wrapped around the part of it. Okay, but so in this core we cut a section of it out, and we mount that piece that we cut out on bearings with a shaft, so it allowed it to well, the arrow goes this way. It allows it to rotate like that, you see. And so if we position this rotor part of this on the shaft vertical like that, so that this is setting in there and this is setting in there, we have a minimum air gap in the circuit. We only have a tiny little air gap there and a tiny little air gap there. And so if we measure the inductance of this inductor, it's going to be quite high, because there's there's very little air in the circuit. It's all the flux is carried by this permeable core, very high permeability as opposed to air. So there's going to be a lot of resistance to the current buildup in this. The L over R is going to be a big number. So we call that inductance the D-axis inductance. Now, if we take that same piece and rotate it on a shaft so the rotor goes this way, we got lots of air in the circuit. And we measure the inductance on the coil. Now the inductance is the quadrature axis, because it's 90 degrees from where it was on the direct axis. So you try to measure the inductance of the circuit when this arrow is pointing into when it's vertical like that. Whoops, I went too quick. Then you have a very low inductance. So the torque that's produced by a reluctance of the machine is only an attracting force. There's no repelling force at all. It's only the attraction of this rotor to this stator. And it wants to align this. It wants to, so you turn this coil on when the inductance is low, when it's in this position. It causes it to rotate, so you turn it off when the inductance is high. When you're generating, you do the opposite. And for example, when you're generating, you put a little current, you allow a little current to flow, a little low voltage, you put across the coil when you're in this position, and then the prime mover rotates it till it's in that position, and then you open this circuit, and you will get an output that's equal to the input times the ratio of these two inductances. That's what you'll see through the flyback diodes in the power converter circuit that'll go back on the DC rails. You'll get a voltage that's multiplied by this inductance ratio. So this next slide, we're going to conclude this series with, or this lecture, not the series, this lecture with this slide, which is quite interesting. How this started is we had a consulting job where we had a client. I think we designed this client. We had a motor, an 8-pole brushless motor. You see the north, south pole, and a 24-slot stator, and of course the coils are wound from pole to pole to create the same number. It's an integral slot winding. It's called 24 slots divided by 3 phases is 8 coils or slots per phase. So if you got 8 poles, then 8 into 8 is 1. So it's 1 slot per phase, per pole per phase, or 1 coil per pole per phase. Okay, so that's how it's wound. Now, notice that the magnets are glued on there. They're locked in there. They can be dovetailed in, or they can't move. They don't slip. So, but we replaced that permanent magnet rotor with an induction rotor. And you'll notice, first thing you notice is the air gap in the permanent magnet machine is much bigger than the induction. It has to be, because we don't want to waste a lot of magnet motive force or ampere turns magnetizing this circuit across a big air gap. See, in the case of the PM machine, the circuit is magnetized not by the inverter as it is in the induction machine. The circuit is magnetized by the magnets, those magnets we bought, so we get that free magnetic circuit excitation for free from the magnets. So we don't care if the air gap's a little bigger. We're going to show you later what the effects of that air gap are. All it means is if I could make the air gap twice as big, I just got to make the magnet a little thicker, that's all. And I get the same flux. All right, with the induction motor, the current that flows in the stator does 2 things. It not only produces a torque like it does in the brushless, but it also has to magnetize the circuit. And the bigger I make the air gap, the more magnetizing current I need, and the lower the power factor and the lower the resistance. So that's the purpose of having a smaller air gap. Now, the other interesting thing I want to show you, it relates back to a previous slide where we saw the cross-section of the machine that showed the X's and the dots of where the current flowed. And if this is an 8-pole rotor, let's see, I don't know how many bars we have here. Let's say we've got 36 bars. I don't know if that's right, but let's assume we got 36 bars. Okay, so if you got 8 poles, 8 into 36 is like 4.5 bars per pole. So 4 bars are going to make a south pole, and the next 4 bars are going to make a north pole, just like you have the poles here. But the poles are not really there. They're created by the magnetic field that's in these teeth, or they're created by the magnetic field from these bars that links with the poles created in the stator. But so that, remember I told you how the stator field rotates at 60 hertz or whatever frequency, but the rotor has to slip. It has to rotate less than that. So if these 4 bars are creating a north pole, and this rotor is going slower than its synchronous speed, then that means that I got to drop a bar and add a bar as this rotates. So I'm constantly since the poles are slipping, they're not glued on the rotor and not rotating with the rotor, the effect of the current flow in the bars, so the last bar and the first bar are constantly having the current reversed. It's either going into the screen or out of the screen. So that's how it creates the slipping poles. I just wanted to make that point to give you a feel for what the difference is between slip or imaginary moving poles and because we're going to find out later that slippage or that slippage, by the way, varies with torque, the load on the machine. And that's why the induction machine has such a poor torque speed curve, not very useful one, when it's driven by constant frequency and voltage without being able to control the current, the magnetizing current separately. And we're going to study the magic of that later. So that concludes this lecture.